to our webinar, Exploring High-Density Fiber Connector Solutions for Next-Gen Switches. We've seen some of these terabit-class switches on display earlier this year at OFC and at ECOC. The design specs from major network silicon providers have been coming out for CPO connectivity. And in this series of webinars, we've talked about many of the technical and energy-saving features of these designs. So in this discussion today, we'll delve into evolving solutions for high-density connectors and fibers feeding into these switches. So this is the 13th in the series of webinars presented by COBO, the Consortium for Onboard Optics, and sponsored by DuPont Silicon Valley Technology Center. Our webinar today is going to last 1 hour. First, we'll hear from Bulent Kozy, who is Advanced Fiber R&D Engineer at Panduit. And then we'll hear a joint presentation from Yi Sun, who is a distinguished member of the technical staff at OFS, and her colleague Mabud Chaudhry, who is Senior Design R&D Manager. After the presentations, we should have plenty of time for Q&A, so your questions are definitely welcome. Please use the Q&A function below. I'll read through these questions and ask them anonymously. If we don't get to all of the questions, our presenters will get back to you as they can. And if you could please, in your question, ask if it's directed to Bulent or E or Mabud. So with that, let's get started. Bulent, the floor is now all yours.
So I'm a member of our corporate R&D fiber research team. We've been working on optical fiber, multimode and single mode fiber, measurements, connectors, some innovative ideas for connectivity and interface inspection and things like this. So I'd like to basically present to you some connectors, high-density next generation connector ideas from the perspective of structured cabling, which is what we kind of focus on. So the motivation of this talk, as Jim already alluded to, we have very high radix count switches that's available. I am so sorry, I forgot to turn on the video. So as Jim alluded to, we have some very high radix count switches available, and based on CPO and onboard optics. And recently, machine-to-machine traffic, east-west traffic, make up as much as 70% of total traffic in data centers, driving fast-growing market for switches and optical links. So this was reported in a Cisco annual report from 2020. So there was a 51.2 terabit per second capacity switch from Broadcom recently called Tomahawk, and this can enable a 512 100 gigabit per second, 128 400 gigabit per second, and 64 800 gigabit per second ports. I mean, you can see this is very dense number of ports that we're talking about, and very high power consumption if you're using pluggable optics, and high attenuation electrical lanes, again, when the pluggable optics are used. So that's where onboard optics and co-packaged optics ideas, of course, they started because of those needs to address the high power consumption and high density. So OBO and CPO can enable these power efficient links. Efficient high-density connectivity is needed for onboard and switch external connections, servers to switches. And we could use structured cabling guidelines and best practices for the whole network. In this webcast, we will review internal and external connectivity options of next-generation switches based on onboard optics and co-packaged optics. Okay, sorry. So I wanted to first take a few minutes to discuss, to sort of remind us or remember the history of the Consortium for Onboard Optics and co-package optics and so on. So first I wanted to look at the Consortium of Onboard Optics and the onboard optics specification that they developed. The idea of onboard optics is not new. Actually, before pluggables in the late 1990s, basically everything was onboard optics. These Intel, IBM, or other companies, AT&T, they've been making optical systems, optical communication systems on the board. They've been putting the optics on the board, so there was no pluggables. But this is proprietary systems, and there was no standards-based approach before COBO. And actually, that was one of the reasons COBO was established. Recently, electrical and optical densities and increase in power consumption, which means increased cooling needs for high-speed pluggable modules, created some engineering challenges. And to address these challenges, COBO was formed to establish a new ecosystem of onboard optics. COBO's specification was approved in December 2018 for 8 and 16 lane versions of 1x400 and 2x400 applications. And on my slide here, I show a couple of pictures to give examples. On the upper right, we have the logical drawing of what an onboard optics engine would look like. And in the specification, there is 2x400 integrated and 2x400 separate versions of these as well. And on the at the bottom on the right is the connectivity that would be needed, either a connectorized or pigtailed. And on the panel, they would call the MDI based on the media-dependent interface based on article description. And at the bottom, on the left, is an actual picture that shows what it would look like when it's implemented. So this OBO IC would be a separate integrated circuit, separate module with low and high speed connectivity. And again, the optical fiber or optical connectivity to the board would be either pigtailed or connectorized. So after finishing of the OBO specification, COBO started working on co-package optics. This was a white paper that they developed, and it was recently published, where they described implementation guidelines and options, detailed options for co-package optics. There was also a discussion on external laser, which is an added option, which is also discussed in Optical Internet Networking Forum, the CPO option. So this requires some additional connectivity, and especially it may require a polarization maintaining fiber. In addition to COBO, recently Optical Internet Networking Forum, OIF, also started a project on this, and this is a 32 terabit per second co-package optics module for intra-data center switching applications. And the idea is to have 100 gig electrical lanes, 32 lanes, and to support 400G base FR4 and 400G base DR4, also to be backward compatible. So, so when you look at these, you're talking about for the FR4, it's 256 fibers that will go into this this switch, and for DR4 using FR4 using a wavelength division multiplexing 4 wavelengths, DR4 parallel parallel lanes, they would require 4 times, which is 1024 lanes. So on the right hand side, I copied a picture from this white paper, COBO white paper, to show what it would look like. There's the ASIC in the middle, and then your optical engines would be sitting at top of the same PCB, and then you would have these optical fibers that go into the faceplate. the picture on the left shows two different options to do this. And actually, one of them is co-packaged optics. The other one is also called near-packaged optics, or using an interposer. And so with the interposer, rather than putting the optical modules on the same PCB, you put it a little bit away, and then there is another electronic circuit interposer to make the connection. And you can tell the attenuation difference, 7 dB channel loss versus 12 dB channel loss through the interposer. But this could be useful depending on the design criteria. So now I would like to, again, compare pluggable onboard optics and CPO options in terms of technology, applicability, and some others like serviceability and stuff like that. So first of all, let's go through these very quickly, some of the key ones. So signaling, they use the same signaling. So the original 400, the original OBO was based on 56 gig, and now we have 112 gig electrical lanes available. So this is actually, the OIF is based on 112 electrical lanes using so, and there is now, obviously, they're working on the higher speeds as well. So for target reach, the pluggables obviously are very flexible. You could have different versions of these, DR, FR. There's multi-mode version, single mode version. So to address different reaches, short reach, data center, hyperscale data center, intra data center, inter data center. For OBO and CPO, we're looking at intra data center applications only. For optical formats, this is actually, basically, we could say this is agnostic, OBO and CPO, because you could implement these on any of these. Right now, for instance, OIF is working on the DR4 and FR4 applications specifically. Obviously, they're not doing SR4, SR8, but I'm going to sort of also mention this later, but we can include SR4 and SR8 there as well. So connector locations, obviously, that's the design of onboard and the co-package. Pluggables are, at the plane, module plane, and the other ones are on the module. So the key issues that needs to be addressed, engineering challenges, are related with manufacturability, capability, serviceability, module standardization, and the failure or I guess reliability of these modules. So these are some topics that are very relevant to OBO and CPO. So for pluggables, obviously it's a very mature market. So we've been working on making these since 1990s, and and it's very, very mature market. So for OBO, it is the module is outside of the ASIC, so it doesn't depend silicon photonics integration, so there's some benefit there. And for CPO, it's actually on the module piece, of the ASIC, so that requires integration. For serviceability, as I mentioned, this is a big challenge especially for CPO, because you're on the ASIC, and that's a very high, that's a very expensive equipment, and it's difficult to work in that environment. If there's any problem, for pluggables, that's not a problem. You just replace the module. For standardization, obviously OBO has been working on standardizing the onboard optics. but for pluggables, I just put heavier IEEE, but we can talk about fiber channel MSAs for the standardization as well. For the reliability, the module failure, pluggables is of course easy to replace, and for the CPO it will be very difficult to replace, and a complete module replacement might be required in that case. So now I wanted to talk about how we integrate or how we take our structured cabling ideas and best practices and look at this CPO and OBO from that perspective. So on the left, I have 3 different cases that I show. This is for CPO connectivity, where you have a pigtailed, and you have a connector in the middle, and a connector on the board. And then you have the optical plane where you would have your connectivity to the structured cabling. So OVO-CPO internal connectivity creates a risk and challenge for serviceability. Very high density of short pigtails, difficulty cleaning, inspecting, difficulty of fusion splicing whenever there's a problem with these internal fibers. That's why it's recommended to use structured cabling like patch cores, patch panels, and conversion and mesh type mesh cassettes for converting between 16, 12 fiber structured cabling connectivity. And of course, depending on FR4, DR4 application, you would have different number of fibers. Excuse me. Different number of fibers going into the module. So you need to have you need to adjust the number of fibers, maybe some breakout scenarios. So it would be better to do these using the structured cabling best practices, as I said, patch panels and things like this. So in the next slide, I'm going to talk about this mid-plane connector, the second option in the middle, and why that could be a good idea. So if you look at this picture here, if you look at the connection for a CPO to the ASIC, you find out that we may have to have some different lengths of pigtails of fibers, and for installation that could cause some trouble. And to be able to, so there may be some breaks of the fibers, during the installation. So to be able to solve this problem, an idea is to have a mid-board connector, so we can have at least one connection point where we can manage these fibers in a better way for reliability. So now let's go to these connectors, that the high density connectors that we have right now that we could use. There have been some new innovative dense fiber optic connectors recently from multiple manufacturers. Most are not standard based yet. So some of them I list here: MXC, that's expanded beam; MMC, that's from US Connect; SNMT, that's another is dense, very, very small form factor connectors. And I put here some pictures from their website on the right to kind of show how they compare to regular, MTP ferrule in size. So even though they are not standardized, they need to comply with connected performance standards, such as from IEC and TIA. So insertion loss is obviously very significant. Because of these high-speed applications, we're working with some limited power budget. And not just insertion loss, but the optical return loss and reflectance are also important, because we're mostly talking about single-mode applications, DR4, FR4. So these could, cause multi-band interference and, relative intensity noise for the laser. Again, on the right here on the pictures, I show examples from two major vendors that have been very active on working on these, and the MMC and SNMT connectors from US Connect and Senko. And you can tell it's almost 1/3 of the actual faceplate size that you would need with these very high speed, very high high density connectors. You can tell, the pictures on the bottom is showing how many connectors you could put on a 1 RU unit with 1,152 fibers. So here I list, I have a list of connectors, starting from LC and some duplex connectors, MPO 12 and 16, and these high density connectors, to kind of show, first of all, how many of these we can fit on a 1 RU unit, and how many fibers, like in the two applications, 400 gig DR4 and the FR4 applications, 1024 for DR4 and 256 for FR4 applications. And on the right, I also show which ones, the ones that are not standardized. You can see most of these, duplex connectors, MPO 12 are standardized, MPO 24, 32, but the newer ones, they're not standardized yet. So even for MPO 12, we might have some issue with fitting them on a single 1 RU unit for a DR4 application, for instance. That's the point I was trying to make here. Okay, so now I wanted to talk about some of the installation issues for multi-fiber connector, high-density connectors. Starting with, I wanted to talk about the end-phase cleanliness problem. So fiber optic connectors are very sensitive to end-phase cleanliness, obviously, that cause some insertion loss, return loss performance issues, and especially for single mode fibers, this is even worse. And this is a bigger problem for multi-fiber connectors. So our industry has established some best practices, some cleaning methods, and most connector manufacturers, they did a great job of providing a connector out of package that has minimal problems with the end phase. But we think there are some improvements that can be done, and one of them is a larger field of view imaging system in production. So on the right-hand side here, I show an upper picture, upper right picture shows a normal. Actually, it's a pretty good commercially available end-phase inspection tool that shows all of the fibers, but and at the bottom of that is a system that we've developed in-house here at Panduit, where we have a much larger field of view. And so the reason for this would be, in case there are some debris or dust or something in an area where the imaging system couldn't see, and then this was shipped, that dust or that debris can travel to the middle of the connector and contaminate the fibers. So this would be a good way to make sure to improve the end-phase cleanliness and in production. So at the bottom, I took some pictures from a very recent paper that was presented in IWCS that sort of shows the impact of end-phase cleanliness on insertion loss. You have the connectors with the dust, and after cleaning, and in the insertion loss delta IL, the delta change. Let's look at the one in the middle, dust, effect of dust. So 0 means it was a clean connector, and that's the attenuation of, and these different colors show different cumulative distributions for a large number of sort of connectors. And so it's very, very small attenuation difference of X is 0, obviously, at the beginning. And when you, and the point number 1 is when after, after there's some dust or dirt on these connectors. And then 2, 3, 4 is after they're clean. So you can, the point I wanted to make is, even if you clean, the dirt and dust or the debris not always go completely away. So there's still some remnants there. That's why it's important at the production to make this, to make it very clear. So regarding the end phase cleanliness, there is one connector type that could help. That's expanded beam and air gap connectors, and I wanted to actually kind of mention about that as well. So generally, expanded beam connectors have higher insertion loss compared to traditional connectors. So that's why one of the reasons why it took some time for these connectors to come into picture. But right now, there are a couple of companies that are developing these, and although these are not standardized, they are being offered, and they could be used for onboard optics and CPU applications, especially for the connectors that's on the board, because of the area, and because there is really no standards, of those connectors there. So the directionality of the connectors, the adapters have to be very small. So these connectors could be a good application there. Another innovative connector design is using air gaps. That's also, and then I show one of examples here, AirMT from, I believe this is from US Senko. So one issue with these type of expanded beam and air gap connectors is obviously they're complex connectors compared to physical contact. And so manufacturing could be a challenge, because of their complexity, and also they could be more expensive compared to PC connectors. So before I finish, I wanted to ask a question. Opportunities for multimode fiber or multimode waveguides for onboard optics. So in principle, the multimode fiber was not left out of OBO specification, but most of the work has been using silicon photonics and single mode fiber, and the recent OIF specifically targeted DR4 and FR4 single mode applications. So what we think is SMF being single mode fiber being more susceptible, or single mode fiber connectors more susceptible to connected end phase contamination. Are there opportunities to use multimode fiber or multimode waveguides even for short reaches, like reaches below 100 meters, switch to server links, for instance? I mean, VCSEL is more efficient, and it has demonstrated robustness, and especially for contamination and misalignments because of the multimode fiber, 50 micron diameter, and obviously single mode fiber is more susceptible, and expanded beam connectors, might need to be needed, but this may not be needed for multimode. So this is a question: should multimode be considered? Related with that, I just wanted to mention this. I don't want to go into detail, but this is a project going on in OBO, Multimode Waveguide Interconnect System, MWIS. And here, basically, we're trying to replace the copper wires with optical waveguide, multimode waveguide, and to address, again, some of these problems. And I also have here some examples of some contribution from our Panduit team on the modeling of the waveguide that we're considering, and looking at the attenuation, expected attenuation that might be depending on the material and the roughness of the material. So just I don't want to give detail, but this is just another project that's been going on. So in summary, pluggable optical module ecosystem based on IEEE and MSAs has been in place for decades, providing flexible and serviceable high-speed switch optical connectivity. As data rates increase beyond 100 gigabit per second per electrical lane, it becomes challenging to connect the ASIC to pluggable module due to port density, power consumption, and thermal limitations. So onboard optics and co-packaged optics can address these problems by bringing, high bandwidth optical connections very close to the switch ASICs, and by increasing the faceplate density. So we have reviewed internal and external connectivity options for CPO and onboard optics, including new non-standard dense connectors, and addressed topics about optical performance, density, reliability, and serviceability, etc. Basically, use of high-density multi-fiber connectors obviously is needed, and we need to benefit from structured cabling best practices, and we need to protect those connectors close to the active equipment in our installation and service. So that's my talk. Thank you very much for listening. I'd like to thank my team members here, Jose Castro, Rick Pinella, Paul Huang, for their feedback, and also OFS team, Mahmoud and Yi as well. And also US Connect reached out to us again also for some feedback about the dense connectors. I'd like to thank them as well. So back to you, Jim. Thank you.
Okay, great. So now we'll have the presentation from OFS. So introducing Yi and Mahmoud.
Thank you, Jim, and thank Kobo for the invitation. Good morning, good afternoon, and good evening from where you are. You just heard from Bulent excellent review of the architecture and of the next generation switches and high density connector technology. In next 20 to 25 minutes, Mahmoud and I are happy to share the fiber technology. We start from an overview and then highlight with some examples. As Bulent just mentioned, onboard optics and the co-packaged optics, those switch at a segment of a very short piece of a fiber inside the switch box between the module or the OE chip and the front panel connector connecting to the rest of the data center. And that piece of a fiber can be a pigtailed or connectorized or pigtailed with a connectorized jumper. And the fiber large, the number of fiber can be a very large, quote some numbers here. For a switch bandwidth of 51.2 terabits per second, could be 256 fibers for CPO based on FR4, and that number could be over 1,000 if it's based on DR4. And you saw the number of in one RU switch, it could be like up to 3,000 in Bulent's presentation. With that larger amount of fibers inside switch box, a narrow space, the routing of the fiber is challenging, and that requires some tighter bending. For example, of 7.5 millimeter radius at the exit for onboard optics modules. And besides of high density and tight bending, the fiber coupled to the CPO OE chip can experience elevated temperature up to 260 degrees during the socket reflow process. And the CPU can have the option of external laser, and external laser has the option for polarization maintaining fiber. So with the requirement of a high density, tight bending, high temperature polarization maintaining, the question arises for the reliability of the fiber and the optical performance, including loss and MPI by refrigerants. So this slide overviews the fiber technologies. The onboard optics, the fiber for onboard optics and the high density pluggables can choose either the single mode fiber bending sensitive or bend optimized multimode fiber. Same applies to co-packaged optics. The current co-packaged optics 3.2 terabits per second module is based on DR4 and FR4, that's for single mode. But as Bulent just mentioned, multimode VCSEL option is not left out. Multimode VCSEL platform has the benefit of low power and a better connector tolerance that was well proved in pluggable transceivers, and the same benefit can be carried over to the co-packaged optics and the onboard optics. So let's zoom in the icons on the top left, the bending sensitive single mode fiber. Here are the diameters of ITU specified single mode fibers. The G657, A1, A2, B3, I'd like to point out OFS has ultra bending sensitive single mode fiber with bending radius specified down to 2.5 millimeter and macro bend loss less than 0.2 dB per turn at 1550 nanometer. At the bottom shows the reach of the OM345 fibers, laser optimized multimode fiber with 100 and 400 gig and 800 gigabits per second VCSEL-based Ethernet transceivers. So we can see here the reach supportable by the OM345 fibers maintained, predicted to maintain, it tends to up to 100 meter, up to 800 gigabits per second. I like to point out here is 100 BiDi, 400 gig BiDi, and 800 gig BiDi. Those are wavelength multiplexing using 2 wavelengths. And they're also proprietary SWDM4, that's 4 wavelengths. So the bending sensitive design fiber and wavelength multiplexing, those are the approach to increase the fiber density, optical density. And on top of that, there is also reduced cladding, it's called a thin fiber, and the rollable ribbon, that's to increase the fiber density inside the cable. And there's specialty fiber with higher numeric aperture, smaller mode field diameter for optimized for coupling integrate to PIC, and their polarization maintaining fibers for external laser. And for those fibers, the design feature can be overlapped. The reduced cladding can be bending sensitive single mode fiber or multimode fiber or polarization maintaining fiber. And the rollable ribbon the single mode or multimode fiber can be put into a rollable ribbon. And on the right are 2 types of more future looking fiber technologies, multicore fiber and holocore fiber. There are lots of R&D efforts on the multicore fiber. And the holocore fiber is actually commercialized and with a field deployment. Regarding to the OBO, that's very small, short reach, short length of application. The reliability and splicing those bending sensitive of holocore fiber remain to be addressed. From here is 3 slides. I use 3 slides to touch on the fiber reliability. Fiber reliability is definitely not a new topic. This slide reflects on what lessons we can learn from telecom, datacom, and fiber to the home can be adapted to the OBO or CPO. First, in past 3 to 4 decades, several billion kilometers of optic fibers have been deployed in telecom networks, and it has been providing reliable service. And that is done by carry a proof test after the fiber draw at 1% stream to limit the weak point in the fiber, and then followed by a qualification test for optical performance. And the fiber put in field in the cable were designed to experience service stress only 1/4 or 1/3 of that proof test stream. So that's a way to get to warranty extreme low failure rate. And moving to the data center, the fiber can experience service stress higher than that. For example, the fiber in the vertical direction in the structured cabling, several meters experience some self-weight. But there are outstanding studies on this, stress those issues. I quote study back in 2014 at WCS. And in that study, about 20,000 pieces of 10-meter fibers spanning 2 years of qualification tests, and 45 pieces of half-meter fibers agent sample were investigated for mechanical strength and reliability. The key conclusions takeaway from that study was over a 20-year lifetime and low failure rate below 0.4 FITs. Under deployment condition can be a service stress of 1% stream. So to read for this 0.4 FIT, that can be read as one failure for 10,000 pieces of 100-meter fiber over 20 years. And then for the fiber with the tight bands and under tension, both. Those were studied as during the kickoff and through the deployment fiber to the home. And here I refer to one study back in 2008. On the right shows the schematic and the setup, the image of the reliability study. The fiber was put on both a small diameter mandrel and that's for bending, and applied the tension from the top. And the key takeaway from that study is the fibers drop cable can under both tight bands and tension resulting in low failure rate for long service time. So for fiber to home, we know there's tight bands like 90 degree in the corner, and stables that add both bands and tension. So those experience can be adapted to OBO and CPO. And then we mentioned at the beginning, the fiber not only experience tight bands, also a harsh environment elevates the temperature. What's not summarized here, but it's very interesting. There was studied for multiple fiber under elevated temperature for aerospace and automotive and sensing applications. It's not summarized here, but if you're interested, we can provide that in chat or by email. Mabuda gave 2 presentations last year, cover that pretty well. And what is covered here, 2 studies for the specialty optic fibers coating. Back in 2016, Huang studied the coating performance impact on the fiber reliability, and the key finding there is a coating integrity performance, the weakest link in the strength degradation of coated fiber under the harsh environment. We have products that have coatings suitable for various applications, including standard and high temperature polyimide acrylate coat and heat resistant buffers. And in the follow-up study in 2021, there's further extensive study for coated fiber under mechanical optical band conditions and in an emulated environment, particularly for the reflow soldering process. And the findings there is the fibers discolored, but less degradation in nitrogen than in air. And the coated fiber shows the high temperature dual coat is a better choice than a standard dual acrylic coat to use. The table on the right top shows the failure probability over 20 years. And for, with the estimated minimum band radius allowed for 3 fiber samples studied. And special fiber with high numeric aperture, reduced cladding and smaller mode field diameter for optimized for PICs in development. And we are happy to discuss use case. So Kobo recommended 2 cost-effective ways to improve the fiber reliability for tight bending scenarios. One is to double the proof test stream to 2%, and that to eliminate more weak points, and reduce the cladding diameter of the fiber. And here's a figure I put together to summarize several combinations of the fiber cladding diameter and proof test stream, the failure rate and the band radius. The green is with doubled proof test stream to 2%. That improved reduce the failure in time by 30 times. And the red is the reduced cladding, and that improves the failure in time by 6 times. And the reduced cladding reduce resulting less residue fiber stress. That means better mechanical reliability, and also enable smaller form factor for high density solution. However, it brings a challenge on microbending, and that is solvable by optimize the fiber design profile and coating optimization. Here I highlight reduced cladding thin fiber, single mode fiber bending sensitive. It is optimized for on-board optics and pluggable modules with tighter bands, and it's proof test at 2%. It has a diameter, cladding diameter of 80 micrometer. It has excellent microband performance, tighter geometric tolerance, and the cutoffs less than 1260 nanometer. That means less MPI, both O band and S band transmission. And actually reduced cladding diameter fiber is not new. We have a whole family of reduced cladding diameter coupler fiber for various applications, and build up experience for the reduced dimension fibers down to coating like 100 micrometer, and has options on cutoff, coating, and proof tests. The polarization maintaining fiber use a stress rod to lift the polarization degeneracy. There are many polarization fiber products cover the application in a wider spectral range, 840 nanometers, 1310, 14 something, and 1550, and also has different fiber dimensions. And here I highlighted two optimized for the OBO type of applications when standard dimension with bending sensitive. And the key parameters here is proof test at 2% to improve reliability. It has a tight geometrical tolerance, and it's available with a high temperature coating, again, for the reliability improvement. And there's also reduced cladding design. It's optimized for the band loss also, and tighter geometry and low spline loss. And from here, 3 slides on the multi-core fiber. So multi-core fiber has several cores in one single cladding that promise the improve the density by a factor of the equivalent to the core numbers. Here is the single mode multi-core fiber, 4 cores with standard glass OD of 125 micrometer. That has the benefit of compatibility to use the same optical components and equipment to develop for standard single mode fiber over years. And this is a proof test at 2% of strain, 200 kPa SI, that's 2% strain. And we carried a system transmission experiment using commercial 400 DR4, FR4, AR4. The signals were coupled to the fibers through a multi-core to single mode fiber fan out. The rich error-free transmission over 5 kilometer, 10 kilometer were achieved. That's reach specify or exceed that specified for standard single mode fiber in standards. I have to mention splicing technique were developed to apply uniform heat across the 4 cores, a fiber that result in a world record low spline loss. And here shows a multi-mode multi-core fiber, 8 cores arranged in circular arrangement. And we carried the system transmission experiment using commercial 400 GHz 4.2 transceivers And the fiber was in a multi-core fiber assembly. That means the fiber was spliced to fan out, and aggregated 800 gigabits per second. Transmission over the 8-core fibers were demonstrated in distance suitable for short reach optical interconnects, typical for those pluggable transceivers. I'd like to mention again, re-emphasize SR4.2, that's a BADA transceiver, use 2 wavelengths at 850 and 910 nanometer, and 2 wavelengths to double the optical density. And here shows a linear array multi-core fiber, and is preferred for silicon photonics to adapt linear transceiver arrays. And here it is the optical fiber properties. And this is well suited for 100 gigabits per second bidirectional transmission using like a PSM4, and has potential for 400 gigabits per second of future 1.6 terabit communication links. Like also point out for the circular design fiber, the core arranged circular. There's also techniques to convert the circular to linear, to coupling to linear array of a transceiver. And I hand this over to Mahmoud. The floor is yours.
Okay, thank you, Yi. Yi certainly covered several fiber technologies and fibers that are appropriate for the COBO consortium audience and for high density switch interconnects. So I'm going to talk about a couple of issues. The first one is hollow core fiber. Yi mentioned that in the introductory slides. So I'll do a quick animation here to get things rolling. So let me just speak to it, and hopefully I can get through the next slide also. So the hollow core fiber is basically designed so that the transmission guide is through an air core as opposed to a glass core like regular single mode or multi-mode fiber. And essentially, because light travels faster in air than through glass, you get a significant latency advantage. It's specifically 1.54 microsecond per kilometer of fiber. So there's some real challenges in this. The technology that's used for the OFS hollow core fiber is photonic bandgap technology that allows you to, again, transmit through air. So the silica or the glass forms a structure that allows that air guide to carry forward without having issues with PMD, with MPI, with chromatic dispersion, with it's naturally a few mode fiber, and so you have to take care of the higher mode orders, attenuate that, and that's a lot of the engineering that's gone on with this fiber. So the key of it was, the concept is about 20 years old, actually. There's almost 10 years of R&D behind it. As you mentioned, this is not as widely deployed as a standard single mode fiber or multi-mode fiber, but it is commercialized. In 2020, OFS demonstrated a cabled solution for 3.1 kilometer over for 10 gig DWDM with very good BER performance and showed that feasibility. The application has been largest in high performance computing, where even nanoseconds or picoseconds of latency matter. We're also looking at metro type applications and even submarine cable applications to look for much, much longer reach. But from a COBO perspective, we have gotten requests for as short as 20 centimeter type reaches. Currently, the commercial fiber is good for 1 meter or greater, so it would work for jumpers or trunk cables, but it essentially offers the ultimate in terms of low latency for these applications. Okay, there it is. So that was basically just showing an animation, the faster latency. I'm going to go to the next topic, which is rollable ribbon. So this is a cable technology. And again, this is also actually about a 20-year-old concept driven by NTT and several Japanese manufacturers, including our parent company, Furukawa. And what's shown here is basically the concept in this case is a 12 colored ribbon fiber that's partially bonded. So instead of having a continuous bond, it's only intermittently bonded. So what that center diagram shows is that you can basically, with hand pressure, take that flat ribbon structure and roll it into a cylindrical shape. And that gives dramatic improvements in terms of packing density and in terms of a small cable diameter. So it's a high density application. Again, it's been for more within a data center for trunk type cables. It can be for inter-data center, and it's also for certainly much more longer haul or longer reach applications. Just as an example, for a 1-inch duct, you can double the density from a standard ribbon of 432 to 864. So it basically gives you a smaller footprint, which gives you a smaller sort of carbon footprint also. It's a lighter cable. It's been set up for mass fusion splicing. Even though each manufacturer has a different approach, for the 250 micron fiber, a lot of those issues have been resolved even in terms of interoperability. And the next step is to go to 200 micron reduced cladding rollable ribbon fiber. So in terms of summary, again, I covered the low latency hollow core fiber and the high density rollable ribbon cable technologies. And with that, I'll actually go back to Yi in terms of finishing up the summary.
And so we mentioned at the beginning, in the high density solutions, Mabul just mentioned the rollable ribbon, and there are other approaches, bending sensitive design and single fiber, multiple fiber, and their wavelengths multiplexing, BADI or SWDM, and the thin fiber, reduced cladding, and multi-core fiber. That's most future-looking technology. And for the reliability challenge, there's a ways to improve that, increase the 2% proof testing and reduce cladding design, and using high temperature coating. And for the optical performance, I highlighted with those examples with excellent micro bending performance and optimized for fiber design and the coating to improve the micro bending and the tighter geometrical tolerance to for the less connector insertion loss, and the cutoff option for cutoff control for less MPI. And also there's a birefringence control to improve the PR, the polarization extinction ratio. So that summarizes our presentation.
All right. Very good. Well, first, I'd like to thank our presenters today. There's a lot of great information on those slides. They are very information-rich slides. So as I said just a few moments ago, the slides will be available by the COBO website. And this webcast will be available for people to review and share with their colleagues. That should be posted in about a week. We just have a couple of minutes, I think, to wrap things up here. So I'd just like to ask, a couple of high-level questions, 2 high-level questions. First, Bulent, reliability was a key theme in your presentations. And when you look at the designs that are coming up, the CPO designs or onboard optic designs, do you think that there's going to be a lot of maintenance issues that data center operators will have to address in terms of cleaning and things like that? Or are these designs inherently factory packaged so that there will be very little maintenance in these next gen switch designs?
Well, that's an excellent question. Thank you. So actually, I'm going to start with the last statement that you made. I think they should be manufactured in the factory with those connectors, everything put in place, because we believe that it would be very difficult to actually allow technicians in the field in installation environments to sort of tamper with these the onboard connectors you remember the number of fibers that we're talking about in that 1RU sort of switch unit, and we're talking about a very expensive switch ASIC equipment, and it would be much better if these are done in the factory, and then the technicians in the field, when they're installing the structured cabling environment, they only deal with the the plane, the connector that goes to the plate of the equipment, just like a pluggable pluggable equipment. The first part of your question, yes, I think definitely this is a like serviceability or reliability issue, because these things you can imagine something's gonna go wrong and they need to be serviced. And I don't know if I mentioned this, but I actually heard from a couple different people in the industry about how scarce we have the technicians, that the highly trained technicians in the field. And I mean, this is I shouldn't say scarce, but there is a lack of highly trained technicians, even without the co-packaged optics or onboard optics type equipment. Now, when you include those, I think it will be even worse.
Exactly. The maintenance issues and reliability issues could very well become the data center operator's major problem.
I think so. I agree. Yes.
So I want to jump over to OFS and first a quick question from the audience: how many fibers can Furukawa form into a linear array max?
For this question, we are happy to hear what is the use case requirement for the maximum linear array.
I think probably these switch designs that we've been talking about, where you have the ASIC and then the co-packaged optics on the outside, and you're talking about hundreds, thousands, perhaps, of fibers that need to be aggregated. Could those be put into that kind of linear array?
I think the linear array, I'll bring this question to my colleague who has more expertise on design this type of fibers. And my own feeling of this, it's depends on, because the switches, we have 1,000 fibers or connectors ports over there, but it actually each one has based on the 3.2 terabits or 400 gig ports, so that would decide the maximum number of.
Okay, and one final question, and that's a similar one. When you look at that switch design of the ASIC and the CPO, and then you see how the fibers are coming out there, the bends that they have to do. Would you be considering that to be one of the high stress type environments where you would end up with some questions between the different fiber types, which one will be the most reliable? Or when you see that type of design, is the fiber connectivity challenge a difficult one in your opinion, or this is something the industry is solving?
So for this, if I understand you well, so where the high stress, the bending is for the fibers for the OBO and the CPO. We know this OBO, CBO is still very new, so there are different ways to handling from different manufacturers, still in developing stage. And the numbers I read from the COBO white papers, like 7.5 millimeter bending radius at exit. And I heard some numbers like if you have the grating coupling from the top to the PIC, and then like a 3 millimeter radius. So those are all high stress part of the for the fiber and the reliability over there.
Yeah, Jim, I'll quickly add, I think what you presented there, OFS does have an easy bend fiber, a single mode, that would meet those requirements on the single mode side. There's a lot of optimization on the multi-mode side also for bend optimized. It would be a challenge or something like a hollow core for something like that. Getting those sort of tight bend for a very short distance would be a challenge, but single mode and multi-mode are positioned for that.
And then there, there's designs newly developed to reduce the cladding diameter and with increased proof test or to and a high temperature coating optimize or to improve the reliability.
Okay, excellent. Excellent. Well, with that, we've reached the top of the hour, so we're going to have to end our webcast at this time. But want to thank everyone in all of our three of our presenters. Excellent job. Lots of valuable information there. Contact information was provided in the presentation, so anyone in the audience who has further questions, please reach out directly to them. I'd also like to thank Consortium for Onboard Optics for continuing this series, and especially the DuPont Silicon Valley Technology Center for your sponsorship. So thank you everyone for attending our webinar, and we look forward to hearing more from everyone in the future. Thank you.